So my name is Alexandre Chabot-Leclerc, but you can call me Alex. That'll be probably easier for most people. Dylan here, my colleague, will be the helper. So if you need help, I don't have little post-its for everyone, but if you go like this, or if you shout help, he will come help you. So our day jobs, we work at Nthought, both of us, and we're Python instructors, scientific Python instructors. So we have the pleasure, we have the answers to the questions, yeah, I guess so, most questions, and the pleasure of teaching NumPy a lot. So that should be a fun afternoon. Who has used NumPy before? Wrote yourself a line of code that uses NumPy. One, yeah, it was precise. Who has used someone else's code that uses NumPy? Okay. Who would not consider themselves a Python programmer first? No, it's not identity-based or anything, but like, who's like a MATLAB user, let's say? Okay. I hope that won't last. Who's an R user? Handful. I guess who's a JavaScript user? Hello. Anything else? Fortran, I guess. SAS, SQL, yeah, okay. What about you? Yeah? Stata, okay. C and C++. All right. Yes?
Fortran 77. 2018.
Okay, well, good. I'll do the best. Nice. So there'll be a little bit of everything for everyone. Since there's a good number of MATLAB and Fortran users, I'll talk a little bit of like there are fundamental differences in how they store, how NumPy and Fortran and MATLAB store memory, and how they think about multi-dimensional arrays. So I'll spend a little bit of time making sure that that's clear for everyone. Yeah. So, ready to go? Okay. So I'll be using slides, a mix of slides that you should have. I think they were on the GitHub repo, and I'll also go in the interpreter, type some stuff. So interactively build bits of code. You're welcome to follow along, to type along. It's like a code karaoke session, and you're also welcome to interrupt me with questions. And if I repeat your questions, it's not because I did not understand. It's for the benefit of posterity and the future YouTube listeners who will maybe watch this video one day. So chairs should arrive eventually. Okay, I will start off with a little justification of why we would want to use NumPy. So just a quick word here. I'm using Canopy for where I'm going to write the code, solve the exercises. Nothing special is happening here. On the right-hand side is just a regular IPython prompt. On the left-hand side is just a text editor. If you're doing this in Jupyter, you can follow in Jupyter. It'll be fine. If you're using Spider, it'll also work fine. Or if you're using Emacs and a terminal, it'll also work fine. Only when we do the exercises that are in plain Python file, I'll show you a trick if you want to solve them in Jupyter, so you can import the content of those files to do the exercises. But for the most part, I'll just be typing in here, and you're welcome to type along. So I'm going to start off in a world without NumPy arrays. So I'll create, just for the sake of discussion, a little two lists here of integers. Right. Each of them has the same length. And let's say we want to add those two lists together. Because of how the language works, the plus operator does not mean add those two lists element by element, but rather it's a concatenation. So that won't work. If I want to add them together, I have to write a for loop. So something like this. So both of my items, that would zip my two lists together, Oops, I forgot something here. So I would have an empty list that would initialize. I would loop over my two lists. And that would do element by element addition of my two lists. That's kind of verbose. You're welcome to type this, but the whole point is that we don't have to type this, right? But if you're working with plain lists, or if you're, for some reason, like you don't want to have NumPy as a dependency, or you're not dealing with much data, it's like a little project that has to be a single file or something, that's okay. We can make do, but it's kind of tedious. And also in the grand scheme of computing, it's kind of slow. So to give you an example of how slow it is, so I'm going to create another list of integers here. 1, 2, 3, 1, 2, 3. So 1,000,000 integers. And I will use an IPython magic. So it's a command that starts with the % symbol that is not part of the Python language. It's part of IPython itself. And it allows me to basically run a line of code a bunch of times and start a timer, run it a bunch of times, stop the timer, and then calculate how long each iteration takes. So I'm going to calculate how long it takes to sum this 1,000,000 integers. And it's about 7 milliseconds per loop. So 7 milliseconds for us humans is fast enough. But it's very slow compared to how fast like the computer could do it. So what I'm going to do, I'm going to bring in NumPy and see what we get out of using NumPy. What's the benefit, both in speed and in sort of expressivity. So throughout this exercise this afternoon, I'll work with NumPy imported as under the name NP, just a common shortcut. Instead of typing numpy.array, numpy.sum, numpy. The various functions we want to use, the NP prefix is just think of it as a nickname for the NumPy module. So while we're on the topic of speed, I'm just going to get that out of the way and we're going to have a good argument why we should be using NumPy. So I'm going to define a new variable. I'm going to call it garray. And I'm going to pass my list G that I created earlier into the array constructor. And NumPy is going to take that data from a Python list, put it into an array. And then we're going to get into how that works in a little bit. But instead, let me do it this way. I'm going to use the sum function, not the built-in sum function in Python, but rather the NumPy sum. I'm going to pass in my array. And there we go. So a little benefit here, kind of one order of magnitude. It's not too bad for no effort, basically, right? Just because we're using a different data structure, because we're using arrays, we get extra speed. Does anyone know why that's happening? Why is it faster? Yeah?
Because NumPy is optimized for single type numbers or like string, if it's just all one string or ints or floats.
Yeah.
Optimized for each variable type.
Yeah. So Python lists, so this list here, basically the way it works is think of it as the container, the list. What it contains is a bunch of addresses. So it's like a notebook or like an address book with your friends. The address book itself doesn't contain friends. It contains addresses of friends, and then you can send them emails and invite them to your party. But that's kind of tedious. You have a bunch of back and forth, scheduling the party, that kind of stuff. You have to get everyone into the room. Whereas what NumPy does is that it takes all of these numbers and puts them all together into one room, into one data structure, into one memory buffer. So those integers are all together in memory, and they all have the same type. And NumPy is then able to do very, very fast computations on those numbers because it doesn't have to do type checking. It doesn't have to get to to ask all the get access to all the objects. It has all of them right there. So let's talk a little bit more about this expressivity. So I'm going to redefine my two arrays A and B. But this time, instead of defining them as lists, I'll define them as arrays. So np.array is the array constructor. Within the array constructor, I'm basically putting my list of integers. So I'm going to do that for A. I'm going to do that for B. So now I have two arrays, A and B. When I look at them, IPython shows me the representation of those arrays. It omits the NP prefix. It just says array, but it's how we differentiate between a Python list on line 12, for example, and a NumPy array on line 15. And now if I add my arrays A and B, NumPy is basically doing the for loop for me of doing the point-to-point operation. It'll take the first of A with the first of B, add them together, second of A, second of B, third of A, third of B, etc., etc. And that kind of point-to-point or element-wise operation works with every single operator. So multiplications are also point-to-point. Divisions are also point-to-point. Exponentiation, also point-to-point or element by element. All right, let me go back to the slides for a second. So the slides starts, so I know this is a tutorial about NumPy, but the slides start with Microsoft. This is not a good moment. I'm sort of busy. They start with a section on matplotlib. I will cover matplotlib for 5 minutes a little bit later before an exercise. We're going to use it to visualize the arrays. So I'll jump over this and go straight to slide 18, which is the introduction of the array and what's special about it. So our array, we start off by just creating a simple array like I've done earlier in IPython. The type of that object is numpy.ndArray. The nd stands for n-dimensional, multi-dimensional arrays. For now, we're sticking to 1D because it's easier to reason about. We're going to introduce most of the topics in 1D. We're going to do a little bit of 2D. And then for 3Ds and higher, I'll just explain how it works, but we won't really work with that this afternoon. So what's particular with our arrays? So I mentioned that the array kept all of its data together. And as our friend over there said, what's particular about NumPy arrays is that it's homogeneous, is that every single element of the array is of the same type. So every single element is an integer of, let's say, 32 bits, or it's a floating point of 64 bits, or it's a positive integer, an 8-bit unsigned integer, so a value between 0 and 255. And that type is accessible as an attribute in our array called the D type, short for data type. So in this example here, my array has 4 integers, and the D type of that array is int 32. The D type you get will, by default, will depend on the platform you're on. If you're on Mac or Linux, you'll get int 64. If you're on Windows, because of the way Windows works, you'll get a 32-bit integer by default. But we'll talk a little bit later about how you can control that if you want. Our arrays, because they can be multidimensionals, one of the pieces of information that the array will keep track of is its number of dimensions. So that's accessible as an attribute named ndim. So this is 1D array. And then it has what's called a shape. And the shape is one of the most important attributes or metadata kind of about your array, is what defines how it interacts with other arrays, basically. So I'm going to go back to IPython here. So my array A, like I said, it has a number of dimension and it has a shape. So shape is an attribute. It's not a method. it's attached to the object, but it doesn't take parentheses. It always returns a tuple. So it's one of these objects here with parentheses and the trailing comma. And this is the number of elements along each dimension. So my array here has 1 dimension, and dim is 1, and that dimension has 4 elements. And we're going to see in a second what happens if we have 2 dimensions.
Why does it have the trailing comma?
Good question. So there is a type in Python called an integer, right? And there's a type the type of this object f is called a tuple. But the tricky bit here is that what makes the tuple, a common mistake is to think that what makes the tuple a tuple is the parentheses, but it is not the parentheses, it's the commas. So the number 10 in parentheses is just the number 10, but the number 10 with the trailing comma is a tuple. So it's just a tuple with 1 element. The parentheses are there because visually it's easier to group together as a single entity, and it's kind of easy to miss the commas. The parentheses are often there so that when you're visually scanning from left to right, you spot the parentheses and then you go sort of further scanning for the commas. So yeah, the shape will always be a tuple, even if there's just 1 element. If there are multiple dimensions, basically this tuple will have as many elements as you have dimensions in your array. All right, so my array A here, and my array B, sorry. I have demonstrated that I can multiply them together. I can also multiply by a constant. And NumPy will happily do something called broadcasting. It will apply my transformation to every single element in the array. So there is a for loop happening somewhere between our fingers and our CPU, but we're not writing the for loop, which is why, which is important. That's one of the reasons why NumPy is fast. We can do without the NumPy for loop, the Python for loop machinery. And the other thing that NumPy brings, so it brings us all of these mathematical operations, the array data structure. It also brings in a bunch of functions to compute things like the sign of an array, which will compute the sign of every single element, or the natural exponent of every single element of A, or the natural logarithm of every single element of an array. These functions, they're also written in C. They're part of NumPy. They're very, very fast. Their name is called a universal function, or sometimes you might see the word ufunc. Oops. So np.log is a ufunc. So whenever you see this, it's a little hint that you're not looking at a pure Python function anymore. You're looking at a NumPy function. So np.sum is a, well, it doesn't tell you ufunc here. It tells you where it's from, but at least now you get the hint that this function is from NumPy and not from Python itself. All right. So our NumPy arrays, they are what's called mutable, meaning that we're able to change their content. We'll be able to pick an element at a given position, and we're going to be able to set an element at a given position. So in the upper left here, I'm selecting, given this array here of 4 integers, I'm selecting an element, I'm getting an item at position 0, which is the first element of the array. For the MATLAB users over there, everywhere, MATLAB users everywhere. Just a reminder that NumPy, just like Python, uses zero-based indexing. So 0 is the first element along a given dimension. So I can get an item. I can also assign to a given position that will modify the memory in place. So in this case, I'm replacing whatever was at position 0, which happened to be a 0, with the number 10. One very, very important piece of information, important behavior, is that given the D type of an array, so this array here is an integer array, if I try to assign something that's not an integer, so either by assigning a float here, or I'm trying to fill the array with some kind of floating point value, it'll simply be truncated. So Python is NumPy is very, very strict about the kind of data you're putting in there. If you set it as a float, it'll coerce anything that comes in to be a float. If you define something as an integer, it will coerce everything to be an integer. Good or bad? Good, because predictable. Bad, because not flexible. So if you're coming from, let's say, MATLAB, or like arrays are all float all the time, why would I care? Sort of. I'm in the middle. It's neither good or bad. It's just how it works. So knowledge is power. Now that you know this, you won't be surprised if your data gets truncated or its type gets converted. Yep.
If you define an array, like let's say you define a third array like C, and you just start typing elements, does it define the overall array structure by the first element, or how does that work? Because when you defined it in B, you didn't say what the type was, but you just put integers in.
Yep, good question. So the question is, when I define an array, so let's say I define this array A here. Again, I'm going to define a bunch of array A's, I'm sorry. How does NumPy decide what the type of the array should be? So the rule is, it will be sort of, if you think of the pyramid of numeric pyramid, how's it called? The hierarchy of numbers is also called the pyramid. So if everything's an integer, the D type of the array will be int. If one of them is a float, the array will be a float. And if one of them is complex, the array will be complex. So it's not the first one, it's not the last one, it's any of them. But we might as well talk about this now. There's an argument to the array constructor called dtype. Notice the pattern. It's called dtype as an attribute. It's called dtype as a keyword argument, where you can enforce a certain type. So look at this here. I say, yes, I'm passing in a float, but I want to enforce that this array should be int 32. And then NumPy will use that particular dtype to allocate the array, to create the array. So you have control at creation time. Sorry. A will look like this. So whenever you have a non-default dtype, NumPy will show it to you. So if it's int64 or float64, it won't show you the dtype. But if you change it for some reason because you loaded it from disk, result of some transformation, some casting, it will tell you this is not the usual one. You might want to be aware that this is different. Mm-hmm. Good question. All right, so let's move on to higher dimensions. So I'm going to define an array C, which has 2 dimensions. And the way to define one of those by hand is basically as a list of lists. So in most cases, we'll get arrays as the result of doing some computations, as the result of loading data from disk, or we're going to get arrays from places. It's not that common to write them by hand, but for the sake of keeping it sort of self-contained, I'm going to create this array by hand. So I open 2 sets of square brackets. So I'm going to have one list inside of another list. The first list is going to be my first row. And my second list with 20, 21, 22 is going to be my second row. So be sure to close all the brackets, close all the parentheses. And then when I look at my array, NumPy together with IPython are being kind, and they're showing to me sort of a nice representation of my array, where instead of having it all flat, it makes it clear which one's a row, which one's a column. So this array C has a D type, right? The D type is something that doesn't depend on the number of dimensions. There's always one D type. So also an integer 64. My number of dimensions, this time we have 2. And then my shape, still a tuple. And now this tuple tells me there are 2 elements along the first dimension and 3 elements along the second dimension. All right, so we're learning a thing here. The first dimension, or dimension 0, is rows, the number of rows, and when they have the second dimension, or dimension 1, is the columns. So I'm gonna just give me a second. I'm going to draw this on screen on the whiteboard, so we have a reference of this for a little while. All right, so what I drew here is basically the array that I have on screen. I drew them just as little boxes, kind of like a table, and the little arrows, sort of the coordinate system in the upper left, says dimension 0 goes down is the first dimension. Dimension 1 goes horizontally across columns. Your question?
So to the earlier question on the tuple with that structure of having 4 comma, does that mean that earlier structure was a column vector?
Good question. The question is, if I have a one-dimensional object, does it mean that I have a column vector? No, is the short answer.
Does that mean that there's no need for that answer, or we don't know? Or?
So NumPy, like the C sort of family of languages, is row major.
Okay.
So it means that the basic unit of contiguous elements of memory are on the same row. This is the total opposite from Fortran and its descendants, so mainly MATLAB, where the basic unit of memory is a column.
But can you switch back and forth? Can you take a structure that's a row and turn it into a column to get your linear algebra right?
Yeah. We'll talk about that later. In order to turn a row into a vector, I would need, that object will need to have 2 dimensions. So basically its shape will become a 5, let's say a 4, 1. And then you can go back and forth. But if you have a one-dimensional object like my array A, doing a transpose of it doesn't make sense because there's no second dimension where to go. It's a tricky thing. So the important part here is we're dealing with arrays, not with matrices. So if you're coming from MATLAB where everything's a matrix, this is not the case here. The basic element is a one-dimensional array, then 2, 3, 4, 5, 6, but you don't have, by default, these 2 dimensions all the time.
Okay.
So word of warning, speaking of matrices, if you read the NumPy docs, you'll see that there's a type called the matrix type. You should not use it. Even the NumPy docs tell you not to use it. They're actually deprecating it, I believe, they will remove it from NumPy. Everything you can do with an array, you can do with the matrix, but the opposite is not true, and there was a bunch of weird behaviors. So you can forget, wipe from your mind the existence of NumPy matrices. Just, they don't exist. But they do, but they don't. All right, our 2D array. What else do I have to cover here? So our 2D array has two dimensions. Its shape is 2, 3, 2 rows, 3 columns. There's another attribute called size. It's not super useful, but sometimes useful. That one tells me the total number of elements. So if you want to know how much data you have, that could be useful. And actually has another friend called NBytes. If you're working with very large data and you're sort of concerned about how much memory you're using, the NBytes attribute will tell you the amount of memory taken by the data portion of the array. Not about the metadata like the shape, the number of dimensions, etc. But at just the numbers basically. So all these values here. So with our array A, we were able to get an element at a given position like this. We're able to set an element at an arbitrary position using the square brackets notation. This also works with two-dimensional arrays, but the way we're going to do this is by putting all of our indices, all of our positions within the same set of square brackets. Meaning that if I want the first row, first column, I'll put all of that within the same square brackets. Something like this. This is different from working with actual Python lists. If I was working with actual Python lists, I would have to write it this way. I would have to chain the square brackets. It will work for some definition of working in NumPy, but I highly recommend, if you want to stay sane and write bug-free code, that anytime you're selecting data or assigning data to a multidimensional array, always put all of your coordinates within the same square brackets. Right, so if you had a 5-dimensional array, you would have some value, comma, another value, comma, another value, comma, another value, comma, another value. So all of that within the same square brackets. What happens if I do partial indexing? So this is getting item at position 0, 0. So that's row 0, column 0. If I attempt to do partial indexing where I pass fewer indices than I have dimensions, what happens is that NumPy gives me sort of all remaining dimensions. Again, different from what MATLAB does if you're coming from MATLAB, where MATLAB would give you the first element. Here what you get, you can think of it as this gives me the first row in this case, or the first inner list. So I get all this subset of the data.
So if you wanted to see a column, could you do like a comma 0?
Yeah, we're going to come to that in a second. The question was what happens if I have a two-dimensional array and I want an entire column. We're going to cover that right now. So I'm going to bring up the slides for this because it's easier to see the before and after. So if you're following along, it's on page 23. So what we're going to talk about here is this operation where we want to subset some data. A subset of the array is called slicing. And the idea is that it allows us to specify a lower bound, where to start our selection, an upper bound, where to stop our selection, and then an optional step size. So I'm starting off with this array A here again. So 10, 11, 12, 13, 14. And my first selection is from position 1 to position 3. The very important thing here is, just like in plain Python, the upper bound is not included. So this means that when I read this, I know this slice, the resulting array will have 2 elements. Right, 3 minus 1, that's 2. I know I'm going to have only 2 elements. So I get the 11 and the 12 here.
So there's no difference in one dimension between normal Python slices?
No, in 1D they behave exactly the same way. No surprises. Slicing, the question is slicing the same in Python lists and NumPy arrays in 1D? And the answer is yes. Everything you know about slicing lists also works here. So just like lists, negative indices also work, meaning that negative indices are positions relative to the end of the array. So there's no special keyword to specify the last element. It's just the integer -1. So in this slice here, we start at position 1. So that's the number 11. We go all the way to -2. The upper bound is not included. So that also gives us a slice 11, 12. For me, though, it has an entirely different meaning. When I read a slice that says 1 colon -2, I read this as drop the first element from the front and drop the last two from the end. And how many elements am I going to get out of this slice? I have no idea. It depends on the size of A. Right, so these, I think of the positive and the negative indices as relative to the edges. So the positive is relative to the left edge of the array, and the negative number is relative to the right edge of the array. Whereas if you pass 2 negative or 2 positive integers for your slices, both of them are relative to the same side, 1 and 3. So I know I'm going to get only 2 elements out of this. And that last one, just don't do that. So you're going from a negative index to a positive index, and it hurts my brain every time I have to think about this. So this will work as in like your slice will contain something as long as the -4 is sort of further left than the +3 is, right? Because you start 4 positions from the end and then you go up until you hit the 3rd position from the front. Even in words, it's terrible. So it works. It's fair game. It's fine. It might happen in a weird, like if you're doing some kind of window processing and you have like increments on window size or something, but this should not be the kind of notation you reach for sort of by default. If you do, I can't help you. Yeah. Then on the right-hand side of this slide, we talk about what happens if we omit some of these indices. So I know that some of you that will say, okay, if I start from the beginning, I'm always going to put the number 0 because that's how it works in my language. That will work fine, but when using Python and using NumPy, it is very, very, very common to omit the indices if they're sort of redundant. So in this first slice here, where I'm getting the first 3 elements, I'm able to just say :3 instead of saying 0:3. You can save your precious fingers by omitting the 0, and maybe it'll seem weird today, a little bit less weird tomorrow, and within a week or a month, you'll just do that all the time. You'll see it everywhere. So that's a common pattern to omit the lower bound if you want to start from the beginning. Similarly, to omit the upper bound if you're going all the way to the end of the array. So this second slice is also a common pattern to say select the last 2 elements of the array. So think of it as sort of a tail in my array. And then that last one here, another common pattern to subset an array, but every other element, it could be every 3rd element, every 4th element, etc., to say I want to go from the beginning to the end in steps of 2. All right, so if you want to skip elements. So that's in 1D. Let's have a look at what happens if we're doing it in 2D. So this starts to be fun. So what's happening here is we're mixing, so we're going to start off with the orange selection here. So within the same square bracket, we're mixing an index, so just position 0, so that would mean row 0, and then 3:5, meaning a slice from column 3 to column 5. Column 5 is not included. That gives us these 2 elements here, 3 and 4, the slice here. Then second one in light blue, where we select the bottom right corner of this array. This is a 4:4, meaning from row 4 until the end, from column 4 until the end. How many elements we're going to get out of this depends on the size of A, because both of them, they go all the way to the end of the array. So in this case, we end up with only a 2x2 array. Third one answers your question. How do I select a column? So the very common pattern and the right way to do this is to just place a colon here to say, I want everything along that dimension. So that would mean all the elements along dimension 0, which is the rows, of column 2. So that would select this entire column here. So one thing to realize is whenever we do an index in our slicing or subsetting operation, we end up dropping a dimension. Right? So I start with the first one here in orange. I start in 2D. I index once, so I end up at 1D. In blue, I slice twice, so I keep all of my dimensions. And then in red, I slice once, I keep that dimension. I index once, I drop that dimension. So one way to reason about this is if you have a Python list, just plain Python list. I'm going to go to IPython for a second. So you have a plain Python list like this. If I index, so if I get one element at a given position, I drop a dimension. Right? I go from one-dimensional object, the list, to a zero-dimensional object, basically just an integer. Whereas every time I slice, even if my slice contains a single object, a single element, so here :1, because I'm slicing, I still have a list, I still stay as a one-dimensional object. Right? So every time you index like this, you drop a dimension. Every time you slice, you keep that dimension. So the orange, there's an index, we go from 2D to 1D. The blue, we slice twice, we stay in 2D. The red, we slice an index, we drop a dimension, we end up in 1D. And then the last example here in darker blue is to select this sort of checkmark pattern. So this means from row 0 until the end in steps of 2. So every other row, the other way to say this is every other row starting at row 2. And then for the columns, we go from the beginning to the end in steps of 2. So every other column starting from the beginning. Any questions before we do a short exercise? Okay. So on the next page, 25, I'm going to leave that up. So there's a little bit of code at the top to create this array. So the idea is that we create an array of 25 integers, and then we reshape it to be square, to have 5 rows and 5 columns. And then I'd ask you to select the 2 columns in red, the last row in yellow, and then this light blue checkered pattern. So I'm going to give you about 5 minutes for this. And we're also going to take a break. So what I suggest is it's 2:15 right now. Is that right? No, never mind. I'm going to give you 5 minutes, and then we're going to look at the solution, and then we're going to take a break. Alrighty. Let's have a look at the solutions. So let's start with the red. So red is, how many slices do I need to do here? 1 or 2? 2? 1, 2? I saw a few ones. Why 1?
Because you're indexing the column, as it were. You're just slicing along the rows.
Ah, okay. So for you, if I do this,
That's called not a slice.
it's a slice or not a slice? It's actually a good thing. So every time there's a colon, it acts as a slice. So like the act of slicing is to put a colon, basically. So the solution is a colon here for the first dimension. That means every single element along the first dimension. In this case is every row. And then what's the slice along the second dimension?
What colon going to?
Yeah. So let's start from the beginning. We don't want the first column, which is 0, but we want the second one, and that's a 1. I need a colon here, therefore I'm slicing. Let's sort of skip over the end end index and look at our step size. So it's a step size of 2. Do we want to stop before the end or go all the way to the end? In this case, I would go all the way to the end, because like this, expressing this slice 1 colon 2 gives me the 2 columns that I'm interested in. I could put a -1 in here, but it sort of means something different to me. If I put an upper bound, it means that I will never include the last column. Whereas if I don't include the upper bound, it's just keep on going for as many columns as you have. I'm not picky. So I'd be satisfied with this red selection here. I'll try to make some space. So red would be this. All right, what about yellow? There's actually a lot of choice here. So I heard someone who said just 4, and that would work, right? 4 is the last, so 0, 1, 2, 3, 4, the last row, the last element along the first dimension. NumPy is going to give me everything remaining along the other dimension. So yellow is is what I'm looking for. Oops, sorry, yellow. Does anyone have another suggestion for yellow?
4, colon.
Yep, all of the above. So yellow, I can do a -1. That would also work. That would be the last row. Again, it has a slightly different meaning to me. The -1 always means the last row. Row number 4, always the 5th row. And if I have 1,000 rows, it's not necessarily the last row. So depending on your algorithm, what you're trying to do, the selection, one of them is better than the other, is more flexible. And someone said I could also slice along the second dimension. That's true. It's sort of not superfluous. It's unnecessary, but it has the benefit of conveying to your users, probably your future self, that this array should probably be 2D. So it has benefits, even though it's not required. It's informative, and informative is good. So all of these would work. And obviously the 4, colon would also work too. So yellow, 4, colon. So these 4 work perfectly. And then for what's the answer for the blue one, the blue selection?
You want to go by 2, starting with row 1.
Yeah. So that's actually a good point. You can start wherever you want when you write it down. Like if you look at this, I know the step size is going to be 2. Let me figure out later what the offset is. So I look at that. It's not the first row, so I'm not going to put a 0 here. It's the second row. So I put a 1. Do I go all the way to the end?
No.
Mm.
Oh, and this one, yes, that's good.
Yeah. So I'm looking along the first dimension here, the rows. And whether I stop at -1 or I go all the way to the end, I'm going to get the same selection. On the other side, though, when I look horizontally, when I select along the second dimension, what's my slice here?
-3, colon, -2.
Interesting.
Colon 4.
Yes. So let's start with the thing we agree with. So everyone agrees that the step size should be 2. Everyone agrees that we're going to start from the beginning. Some people say we start from the beginning, I don't need to put anything. Some people say we start from the beginning, so I'm going to put in a 0. Some people say I will start with the negative index, so that's -1, -2, -3, -4, -5, which is not incorrect. But again, it's the kind of slightly crazy way of doing this. So even though it is correct, I do not really support this approach. So right? -1 is the last column, -2, -3, -4, -5 is the first column. But that's too much work for my brain. So that's for the beginning. I'll just omit it. We start from the beginning. For the upper bound, we have a little bit of choice. So we can do -1. That would work. We could do -2. Right, because the upper bound is not included. We could do 3, or we could do 4. And in this case, I really don't have a good argument. For one versus the other, it really depends on how you're thinking about your problem. So this would work. I'll readjust everything here. So this one would work. 4 would work. -1 and -2. Yep. Yes.
I was also tinkering, and for the column I put in parentheses 0, 2, and it actually pulled out the 0 column and the 2 column. Is that,
The question is, what happens if you start grouping these slices and indices in parentheses? We're going to get back to that after the break. It's another form of indexing called either masking or fancy indexing or Boolean indexing. It has a few different names. In NumPy, it's typically called fancy indexing. We'll see that after the break. It gives you a lot of control of selecting arbitrary data anywhere in the array. Yes?
Looking at the red selection.
Yes.
We're now selecting columns. Is this slower than selecting rows? I mean, would it make sense to first transpose the matrix and then select rows? Or, I mean, how fast is it? I mean, as you told, it's row-based. Does that mean it has to like collect all these the 1, the 6, the 11, and so on? Does it have to like collect it somewhere from memory and then put it somewhere? Or?
Good point. I guess we can talk about this now. So my red selection, which is now 5 rows, 2 columns, I'm going to select the lower right-hand corner, and I'm going to put a 0 in there. Right, -1, -1 is last row, last columns. If I look at red, no surprise. But if I look at A, and I have a 0 in here. So the question, sorry, I'm going to repeat the question, is slicing a column slow compared to slicing a row? If the elements on a row are contiguous in memory, if they're next to each other, wouldn't be like faster if you did a transpose or something like that. Maybe you would need to measure it. Not enough to matter is probably the right answer. You should go for readability first and then measure to see if the bottleneck is whether you're slicing a row or a column. It probably means that either your Python is not the right tool for the job or you're doing something strange with your algorithm. So you should not worry about this. You should just make the slice that makes sense for your application. And the other thing, the thing that I'm demonstrating here is that whenever you make a slice, what NumPy does is to give you a view of the same memory buffer. So NumPy tries really hard in most cases to not give you a copy. It doesn't copy the data. It still points to the same location in memory. So that means that making a slice of a giant array is really, really, really cheap because it doesn't require any new memory allocation other than some metadata about the shape and about the number of dimensions. If we have some time, I'll cover that at the end of the session. Yes?
So the question related to this is the following. So in Python you have ID operators.
Mm-hmm.
The address in memory. Do you have something similar like that in NumPy?
So arrays have an ID as well, the same way.
Yeah, but for instance, for the subslot, for the when you do slicing.
So the array has attributes called flags, which is itself a dictionary that tells me whether this array owns the data. So the red, which is a slice of the array A, doesn't own the data itself. It's owned by someone else. But it also has a .data attribute which are kind of pointers to the beginning of the offset.
So, but this is just a Boolean. Can you have also then the memory address to that particular thing?
The answer is yes. I don't know how offhand, but the answer is yes, because it's possible to write C functions that act directly on NumPy buffers. So you can certainly work with that, but in Python, in most cases, it's like rounding error cases, you will not act on the like you will not care about that memory buffer, but yes, you can access it.
If I directly assign an element of red, do I also change the underlying A matrix?
Yes, the question is if I assign anything to red, do I also modify A? The answer is yes. I just did it earlier here. I basically executed this line of code, -1 equals 0, and that's what caused this 0 here in A. If you absolutely want to make a copy of a slice, there's a .copy method on arrays that will copy the entire memory. But it's safer, but it's also more expensive because memory allocation is pretty expensive. All right, so let's take a 10-minute break until 2:50. When we come back, we're going to do an exercise immediately, another application of slicing, but actually useful. Not that this wasn't useful. Yeah, and we'll talk about this thing called fancy indexing that allows us to make arbitrary selection, not just like with similar step size. All right, so see you in 10 minutes. So in Python, a Boolean is a true or a false, capital T true, capital F false. And here we're doing this rather strange dance of building a Boolean array by hand, which will never happen. But it has the benefit of, one, fitting on the slides, two, being sort of clear what we're doing here. So we're creating an array of ones and zeros, and we're using this keyword dtype, which we've seen earlier, which is a way of controlling the data type of our arrays. We saw I did an int 32 example. That's how you could control the resolution of the array. By enforcing it to be bool, what Python and NumPy, what they do is they turn all the zeros into false and all the ones into trues. So that mask here is used below as a way of basically selecting the same data, the 10, the 20, and the 50. So the requirement, this mask has to be Boolean and has to have the same number of elements, basically the same shape, the same number of elements as the shape of that array. So here that array has, 8 elements, and that mask must also have 8 elements. In most use cases, though, you'll get these masks not by typing a bunch of ones and zeros, but rather by doing some kind of comparison. So here we'd be creating a mask that selects all the data that's less than 30. And the nice thing is that we don't have to care about where that data is. NumPy will basically look at all the elements for us and create the mask. So let me do an example of this. I'm going to go try Python. I'm going to create a new array A with a 3, a -1, a 0, no, a -2, a 4, a -6, and an 8. So here's my array. And let's say I want to find all the negative numbers. So I'm going to make a comparison, A less than 0. This creates a new array of type Boolean. I could give it a name. I'm going to call it negatives. I don't have to give it a name, but I could give it a name. Readability, it's a bit more readable. And then I could use that mask to select a subset of data, just the data that's negative. I could have, in a small context like this, I could have computed my mask straight inside of the square brackets. Why one versus the other? If I plan on using a mask multiple times, then I might as well give it a name so I don't have to recompute it every time. But if it's a one-off, I just want to select data, compute that mask only once, then I can do it in line, especially if it's a simple mask like this. So these masks, right now I'm using them as a way of getting item. I'm getting data, the data at given positions. But I can also use that mask as a way of selecting element on the array where I'm going to put in a certain value. So I'm going to, I think of it as sort of, I take a big piece of paper, I put it over my array, and then I check everywhere where there's a negative number, I'm going to cut a square. So now I can see through my array. Sort of like cutouts to put a tag on a wall, or like a house number on the sidewalk or something like this. So I'm going to cut out a spot for all of the places of the array that are less than 0, and then I'm going to stick a 0 in there. And if I look at my array, now everywhere where I had a negative number, the negative number is gone and it's been replaced with a 0. So it modifies the array A in place, but it doesn't do anything to the shape. And we can compute more complex arrays as well. So I could select all the data in A that's less than 8. Another array that's all of the data that's greater than 3. And now I need to combine them. So I'm trying to select this 4, basically, sort of a contrived example. But I'm trying to select all the data that's within a certain range. Bless you. So I could try to do something like this. So A is less than 8. I'm going to do it the other way. So A is greater than 3, and A is less than 8. Right? That's pretty clear what I'm trying to do. But it's going to fail with the dreaded truth value of the array, blah, 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 blah. So if you've used NumPy for a little bit, you might have seen this thing saying the truth value of an array with more than one element is ambiguous. Use a.any or a.all. And once you've used NumPy for 5 years, then you know what it means. But before that, you don't. So I'm going to cut a shortcut through time, and we're going to talk about what this means. This is caused by this keyword here, AND. The Python operators for Booleans, the English AND, the English OR, the English NOT, they expect, in the case of AND and OR, on either sides, one true or one false, not a whole array of them. And NumPy, when you ask it for this array here, so the result of this mask is the whole array of true and false, NumPy is like, I'm not sure what you mean when you mean true for this array. Is this array true if everything is true? Or is this array true if one element is true? So it's giving you the choice. It's like A greater than, less than 8. There's one false in there. But if I say any, means this array is true as long as everything is true. This array is true as long as there's one element that's true, then that's fine. And we can use the end. But even if we make it work, even if we use the any or the all, it won't do what we want. We're going to end up with one true or one false. And like, that's the moment where we should realize we don't want one value. We want as many values as we have elements in the array. So this whole dance, we don't need it. We don't need this Python AND and this Python OR. We need other operators that are called bitwise operators. And these operators are, I'm going to write it as a comment on the left-hand side here. The ampersand, which symbolizes an and. The pipe, the vertical bar, which is an or. There's a tilde that stands for not. And there's also the useful but not as often used caret that stands for exclusive OR. And so those are called bitwise operators. And the binary operators are AND, OR, and NOT. So very, very close, very easy to get confused between those two things, but very, very fundamental difference. So the binary operator, the binary operators require one true or one false on each side. The bitwise, think of them as like the multiplication or the addition with NumPy. They're element by element operations. This means that I can do a greater than 3 and, but the ampersand this time, a less than 8, and as I expect, there's only one true in there, which is at the position of the 4. So I've combined those two masks together using these bitwise operators. And I have to use parentheses here because the bitwise operators have higher precedence than the comparison operators. That's how life is. So these bitwise operators, super powerful. They're used every time you do masking, both in NumPy, also if you're doing the pandas tutorial tomorrow, or if you use pandas. Whenever you build these kind of complex mask selections, you'll need these bitwise operators. Yes.
Does this mean all these operators are overloaded for NumPy? The less than, the greater than, and the bitwise operator?
So the question is, are these bitwise operators overloaded for NumPy? Yes and no. So I'll open a parenthesis here. I'll try to make it quick. I'm not talking about NumPy in particular. I'm talking about how Python works. So if I have two integers, when I add them together, Python actually translates this to a call to a method named dunderAdd. These methods are called special methods. They're part of the Python protocol. That's how Python works. So if I do, there's a whole lot of them. You see there's a dunder end, there's a dunder boolean. A dunder is usually a short version of, instead of saying double underscore abs double underscore, people say dunder, which for some weird association sounds Australian to me, probably because of Crocodile Dundee. My brain is strange. But it's basically how all of the Python language works. It's implemented in terms of these methods. So my array A has a dunder end and a dunder abs and a dunder add, etc. So everything is kind of overloaded, if you want to say so. Yes?
Could you explain what XOR means and when you might use it?
Yeah, what XOR means. So I'm gonna do it on screen because if I do it on the whiteboard, no one will see it. How do I draw this again? So true, false, true. So much easier on a whiteboard. So for a regular OR, if, oh, this is fun. So regular OR, so the two sides of this table is, this is one side of the operation, the vertical is the other side of the operation. So the truth table of regular OR is this. As long as one of the two sides is OR, as long as one of the two sides is true, both sides will be, the output will be true. Let me say that again. I'm not sure if I said the right thing. As long as there's a true, the result is true. The exclusive OR XOR. It has to be one of the two sides that's true. And I'm going to try to channel my 22-year-old self that did logic at university or something, and I'm not able to, so it's useful. Yeah, if you don't, true, thank you.
That's the logical equivalent.
Yeah,
Not equal to B.
not equal to each other. So they have, yours is basically different, right? Is that word?
Truth value.
Different truth value.
So one is true, but not both.
Exactly.
One or the other, but not both, exactly.
Yeah. Thank you.
Another question?
Yes.
So going back up to, can you scroll back up on the
Yes.
so you did A is greater than 3 and A is greater than 8 and 4 is marked as true. How would you use that to pull out 4?
Yes. So the question is, how would I use this mask that I've built made of 2 parts in order to select something? I could put it in the square brackets like that. So negatives, and this masks, both of them return a Boolean array that has a certain shape. Negatives, I computed it as a less than 0 at some point earlier. How I compute the mask really doesn't matter. It can be super simple or it can be arbitrarily complex, but once I have a mask, I can put it inside of the square brackets to select my data. And like I said, you can give it a name if it makes sense, if you want to reuse that mask for multiple operations, or you can compute it in line here. So I could even have split it into 3 different names, like A greater than 3, another one which is A less than 8, and then do them together, also give that a name. So depending on what you want to reuse, how complex they are, there's very little cost really to saving the intermediate steps, unless you have a lot of data, but it can greatly help readability, especially if your masks are complex. Cool. Yes.
Just a question on the fancy indexing. If you go back up to the red
Yes.
folder we're looking at, yeah. So is there an advantage to doing it this way versus just the colon, comma, parentheses 1, 3, when we wanted the first and third column rather than the slice?
So the question is there a benefit to fancy indexing or to slicing? Is one of them faster than the other? Speed is not really the main worry. It rarely is, unless you're working with lots of data, and you shouldn't assume that one of them is faster than the other. You should measure. The big difference is whenever you slice, you're going to get a view, like we did earlier. So you're going to get a view of the same memory buffer. You're going to see the same data, which is really fast. We're going to see that in more details later, but every time you do fancy indexing, you get a copy. That is the real difference, and the one that really matters. Fancy indexing gives a copy all the time. Slice gives a view all the time.
So is there also a method to find out the indexes of what is mask is true?
Good question. The question is, how can I find the position of the truths in this? Where are they? There's a function called non-zero, where you can pass your array, your mask, and it's kind of like shape. It always returns a tuple. So notice it opens with the parenthesis. There's a trailing comma here. This array here tells me that position 1, position 2, position 4, there was a true in my mask.
So if you would have, like, say, a 2-dimensional one, so you have then also two arrays.
You get a tuple of 2 arrays. That's right. Were you a MATLAB user? No? Okay. So it's sometimes useful if you care about the position, but there's a whole lot of work that you can do by just using the mask directly. So computing the mask to then get the position where that mask is true, to then use the position for indexing, this extra step in the middle of getting the positions of the trues, it's redundant. It's like extra work that you don't need to do because you can use the mask directly. Cool. Good questions, really.
Are the arrays sorted in memory when they are stored, the NumPy arrays?
Can you say that again?
Are the NumPy arrays stored in any particular sorted order in memory?
Are the arrays sorted in memory? I'm trying to see where the question comes from. They're in the data that they're defined. So like my array A, there's a 3 first, and then there's a 0, a 4, a 0, and an 8. If I sort them, then yes, they're sorted. Like it shuffled the memory underneath. But NumPy will store in memory the numbers in the order you give it to them. Does that answer your question?
Yeah, it does.
Okay. Well, okay, yeah.
I assume if you have two arrays of the same size, say A and B,
Uh-huh.
you could mix booleans with them, like A less than 3, B
Yeah.
less than 6.
Good question. So what happens if you have two arrays? Could you do a mask between two arrays? Very good question. So A is an array with a 10, a 1, a 20. Yeah, let's keep it simple. And B is an array with a 2, a 3, and a 20. So if I do a comparison between both, so A is greater than B, in this case I'm going to have one true, but I get element-wise comparisons, just like I got element-wise addition, element-wise subtraction, multiplication, etc. Was that your question? Yep. And then I could use that as a mask somewhere else. Right? Again, what matters is the type of the array. Like basically everything that's a Boolean array, I will call a mask because it can be used as a mask. There's nothing special about this Boolean array compared to another Boolean array or how I got it. What matters is the D type of the data.
How do you find the position of the Boolean array? Which one is true?
Yep.
You had a non-zero for negative. Do you have that?
I had the non-zero gives me the position of the true, actually. So remember, false and 0, they're basically the same, and true and 1 are basically the same. So you can read non-zero as non-false, which is kind of a weird sentence, but that's basically what it's doing. Okay. So I'm going to go back to the slides for a little bit, just to see how it works if we apply this fancy indexing on a two-dimensional array, and if we mix and match with slicing, regular slicing, and also indexing. So first one is kind of funky. In yellow, we're selecting a diagonal. So it is definitely not something we could do using regular slicing. Right? The step size always changes. So we could not express this just with some colons. So what I'm doing here is I'm passing two lists of integers, and think of this as pairwise coordinates for certain point. So 0, 1 is row 0, column 1 is that 1 here. Then 1, 2 is the 12, 2, 3 is the 23, 2, 4 is the 34, 4, 5 is the 45. We're selecting a diagonal just because, but there's nothing stopping you from making an arbitrary selection of like the 1, the 13, the 31, and the 55. Right? As long as you're passing in this case it's in 2D, pairwise selections. If it was in 3D, you could pass basically triplets to get a point in your 3D array. Then in light blue, we're making these 3 slices here. So it's the bottom half of this array of column 0, column 2, and the last column. And at first glance, we might think, oh, we're totally able to do this with the slice, but notice here there's a step of 2, and then there's a step of 3, so we cannot do this with a slice. But selecting row 3 until the end, that we can do with the slice. So that ends up being 3 colon, so from row 3 until the end, and then we pass in a list of column numbers, column 0, 2, and 5. Then the last one, again, it's a little bit weird because we're building a Boolean mask by hand, but again, it makes it standalone. So this means first, third, and last element of this array. And we're using that as a subset of the data we're putting in the square brackets to say we want all the row that are where this mask is true, the rows where this mask is true, of column 2. And here, notice we use one index, one form of fancy indexing, so it behaves kind of like slicing. So we end up with a one-dimensional array. So start with, so this is 1D, 2D here, and the result is 1D. Yep.
So if fancy indexing is creating a copy, you showed earlier how you could set a value using the slice.
Yep.
So how do you do that then if you're doing fancy indexing?
Yes, so if fancy indexing is making a copy, how do you assign to a value? Let me see if I understand the question correctly. So this is my array A. I'm going to create a subset, which is the array A at position 0 and position 2. So it's the 10 and the 20. I can check out my flags. So A owns its own data. And subset also owns its own data. And just to be clear, A is not subset, right? If I wanted to do that programmatically, make sure that they don't share data, I could do it this way. I've just created them, so I am master of this universe. I already know that they don't share data, but I'm just demonstrating this. So now, so A, subset. So if I assign subset position 0 equals -1, then I've modified subset, and array A doesn't care, right? It's just on its own over there. Does that answer your question?
Yeah, I think so. And then if you want to go back to A because you wanted to change something based on the mask, you're just using the mask to change it?
I'm not sure I understand. Can you try again?
Yeah, so if you wanted to, if you go back up to what A was set.
A was 10, 1, 20.
Yeah, and let's say that you're not creating a set, but you're doing a mask. So the mask is creating the subset,
Mm-hmm.
and you wanted to change the first value, of A based on the mask. You then just apply the mask back to the original array.
Yeah, okay, let me see if I understand the question. So if I have an array A, I used fancy indexing to create a subset of that array. How do I modify A again?
Yeah.
You just modify A, like the last position. I'm going to put 100. I've changed A. They're two separate arrays. As long as you keep the name of the array, as long as you can still access that array, that array still exists. You can still modify it, slice it, mask it again, do computations on it.
You mentioned modifying it through a mask. Is that what you meant?
Yeah, that's originally what I
So
was
that's
saying.
having like a mask on the left-hand side of the sign. We haven't seen that.
Okay.
We did that earlier with the negatives, where we assign zeros like this.
But that creates, okay, that actually changes that.
Yeah. So this assignment here that we've seen earlier, negatives here, it could be a mask. It could be a list of positions. It could actually be a slice object. That will modify A in place. I think of this object here, whatever it is, as sort of like the cutout that I talked about earlier. What this contains defines where the cutout is. Is it like regularly spaced? Is it at arbitrary positions? Is it computed based on the data in the array?
Okay, that's what I'm asking you. So it doesn't matter if it's a fancy, if the mask is created
Where this data has no impact here. Cool. All right, so let's do this quick exercise. So there are two parts. The first one, I'm not going to ask you to do because it's basically, the answer is in the previous slide. I'm getting confused with my consonants here. So you already know the answer, but the second one is interesting. I want to select all of the numbers divisible by 3 in this array here. So I'm going to give you 5 minutes, and then we're going to look at the solution. Yeah. So what's the modulo operator, someone said? The modulo operator is the % symbol. No for loops allowed, just in case someone was tempted to write a for loop. I always have to remember, no for loops.
The result of modulator is true or false or the quotation?
So the modulo operator is the remainder after integer division or floor division. It's like a plus symbol.
So percent obviously works on the arrays as well.
Also, yeah. So if you're not familiar with the modulo operator, 0 modulo 2, I'm going to sort of, it's one of those where I'm going to demo what it does, and then hopefully you will infer the actual behavior. So the modulo operator is the remainder after the integer division by this number on the right. So because I have a 2 on the right hand side, then the answer will always be either 0 or 1. So I will let you expand on that knowledge to find a solution to this exercise.
So this is not going to keep any kind of shape. It's just going to give us the numbers that
What does it, I mean, obviously I can look at the picture, but what is the first one? So
The 0 is where your mask is true. Right?
But is that the answer to the question?
Yeah. It is the answer. You're doing the right thing. All right, let's have a look. So my array is at 25. We shape it to be 5 by 5. Here's my array A. So someone said, what's the modulo operator? Which was a big hint that we should probably use the modulo operator. So if you use the modulo operator, the question is now, which number should I use with this? And since the question said divisible by 3, that was another pretty good hint that we should use the integer 3. So if you compute the modulo of 3, the modulo 3 on all the array, what you get is 0s and 1s and 2s. So those are all remainder after dividing 0 by 3, 1 by 3, 2 by 3, 3 by 3, 4 by 3, etc., etc. And every time I see a 0 in here, it means that that number in the original array is divisible by 3. So you might be like, oh, okay, so I'm just going to use that as a mask. And then something very, very strange is going to happen. So now I end up with a 3-dimensional array, and you're like, no, this is not it. Certainly not. I can reason about what happened here if I sit down and think really hard. It's basically like, but I'm not going to do it. But so what is happening here is because I'm not passing in a mask, right? I'm passing it lists of integers, basically list of integers. It functions as a form of fancy indexing where I get lists and subsets of lists and columns, and that ends up giving me 3D. Super powerful, but definitely not what I want here. So interesting, but not quite it. What I want is all the positions of these zeros, and I can get those if I build a mask. How do I build a mask out of this array here? Yeah, I test for equality to a 0 in this case. And that gives me an array that still has the same shape. It's still a 5 by 5. It is of D-type Boolean. And that, now that I have a mask, I can use that to get those items. And NumPy doesn't try to keep these elements in a certain position in the array because it doesn't really make sense. They could be anywhere. So like it's not going to return another 5 by 5 array with a bunch of missing data or with only the elements we want. So it just gives us the data that we asked for as a one-dimensional array. How did that go? Okay. It's easy when you see the solution, eh? Yeah, just a little thing here about the process. Assuming that you know the ingredients, like you know I will need a modulo, I'll need a mask. I will typically, like unless I know exactly the solution, which doesn't always happen, I will build it like this. I go in IPython, even if I'm building a large analysis or something, or even if I'm in Jupyter, I'll create a new cell, or here I'll just type one statement, I'll look at what it looks like, and I will add a clause or an element to my mask. I'll build it, I'll add a little bit more, a little bit more, a little bit more until I'm satisfied, and then I'll give it a name and I'll keep on reusing it. I'll reuse that name in my code. But yes?
Why the result is only in one array, not in two dimensions?
Yeah, why is the result in 1D and not a 5 by 5 array?
Yes.
It's because this mask could be true or false anywhere, like an arbitrary location. And there's no, like, what else would NumPy put in the places where it's not divisible by 3? Right? It's sort of not clear. It could return an array of 5 by 5 filled with a value called nan, which stands for not a number, which is often used to represent missingness.
Can you show how to present in two arrays, 2 dimensions?
Yeah, so let's say I wanted to keep, that's a good question. So let's say I want to keep all the number, find all the number divisible by 3, and I want them in a 2-dimensional array. All right, this is a good dance actually. So my first question is, what do you want in the let's call them cells that are not divisible by 3? Do you want a 0? Do you want a -1? Do you want, there are geologists in the room, I'm sure. Do you want a 999 minus 999.5 or something? What value, or do you want a nan, this number that represents missingness? Nan? Okay. So I'm going to define the trick here. It's a pretty common pattern, actually. I'm going to create a new array. I'm going to make it empty. Empty is kind of weird, but I'm going to make empty-like. So it's a common pattern in NumPy. There's something called array-like, empty-like, ones-like, zeros-like. And you pass in your input array, and what it does is that it creates a new array that has the same shape. But these numbers here are not what I want. The thing that empty does is that it allocates memory for you, and what's in that array is garbage. You cannot trust what it's in there is whatever was in the memory before. It happens to be now something zeros and ones and twos. If I run this again, that might not be what I get. There we go. So that's obviously garbage. Before it was not obviously garbage.
What was your A modulo 3 solution?
Yeah, but I could never have predicted this ever. Well, never say no, never, but like I could not predict this basically. So my output now, I would like to, that's not gonna work, crap. So I've now filled my array with nans, but I have a little problem here, which is that my output array is an array of integers, but nan is a floating point number.
Can you get the positions like we did with non-zero?
Yes.
Is there something that would give us the, you know, the indices?
Yeah, so what let me do that again. This. So I'm gonna make this float. All right, so this is garbage. I'm gonna fill it with nans. So I'm basically trying to create a container that has the same shape as my input. All right, so A is my, I'm gonna put it on this side, A is my input. I created an output at pre-allocated memory that has the exact same shape as the original. And what I'm gonna do is, I'm gonna use my same mask on both sides. I would probably assign it to, let me give it a name. My mask is A modulo 3 equals 0. And I'm gonna say the output for the position of my mask is equal to A for the position of the same mask. So what's gonna happen is going to, NumPy is gonna take the element at a given position in the array A, go put it in the same position in my output. And now I have all my numbers divisible by 3 at their original location in a new array where I have nans where it's undefined. So I will put this code down here so you can see it all at once. But I changed the type, that's right.
Use NP where?
Yes. Convince me.
NP where A mod 3 equals 0, comma A, comma NP nan.
Say that again?
NP where
Yeah.
A mod 3 equals 0, A, NP nan.
Yes. This is not something I was planning on covering. This would indeed work. Let's have a look at the documentation from, I'll just say what it does. So the first argument of where is something Boolean. It's true or false. And if it's true, it's going to take an element from A. If it's false, it's going to take an element from B. In this case, B is nan. So wherever it's true, it's going to take the element from A. Wherever it's false, it's going to take the nan. So we end up creating a similar array. Yeah, good.
And that also
Good plan.
courses all the data into floating point as well. Right?
That's true because of the nan. That's because there's no, in NumPy at least, there's no value that represents a missing integer. So we're sort of stuck. So the world's a terrible place. Thanks for the where.
Don't you get a an integer calculation when one of the operands is not a number? Not an integer. It's not calculable.
Even if you do, if there's a nan, then the array is float. Always. So nan is a valid floating point values. You probably know is a valid floating point value that represents missingness for integer in NumPy and other libraries. There are sometimes ways of representing missingness, but not in NumPy. So that's why you end up with these tricks where, like, when it's a certain magical number, it represents missingness. If you absolutely want to keep it as integers. Yes.
So when I ran a square basket bracket mask or output square bracket mask, I got a one-dimensional array. How come you have to have output mask equal a mask to get the two-dimensional array? What's going on there?
Let me just explain what's happening and see if it answers your question. Okay, I'm not sure I can reword your question. So this line on line 34, this creates a new array that has the same shape as A, but is of type float. I fill it with nands. Then I compute my mask, and I use the same cutout, the same masks on both sides. So output and masks are already 2D. I'm just taking stuff from one side, and I'm assigning that same value on the A side, on the output side. Does that answer your question?
But if you do output mask or a mask singularly by themselves, they both end up being one-dimensional.
Yes, that's, yeah. So if I do output of mask or A of mask, those are flattened because NumPy has no way of, doesn't build this basically. So the only thing it can do is return these elements that you asked for. Do you have a better explanation for that, Dylan?
For the 1D outputs?
Yeah.
So there's no way for NumPy to guarantee that can be broadcast up in any shape. So you can imagine if you start off with a 5x5 array, and the only true elements, there's 3 of them, there's no way to cast that into any two-dimensional array other than a 3x1 or 1x3. And given what you started with, neither one of those is really any more intuitive than just saying, like, here's the flat value of numbers that you wanted.
So by having output mask equal a mask, NumPy is able to determine that it should be a 5x5 array. Basically.
So when you have that assignment operator in there,
Put it on, you're on the spot.
yeah, I'll be on YouTube. I'll be famous. So when you have that assignment operator in there, what really Python is looking at is those locations in memory.
I don't think it's on, dude.
You gave me a bad microphone? I didn't turn on the microphone. There you go. Can you hear me now? All right. So when Python sees an assignment operator, that thing on the left-hand side is not extracting the values and putting them in some flattened copy. Those are referring to the actual locations in memory where those values are stored. So you can assign into all those locations, given that you either have like a single scalar or an array of the same size and shape. Or you can ask for it to give you a new object with those values inside of it, and that's if you just have that blank expression. And it's a little, it's confusing. It's hiding a lot of the complexity of what's actually happening. But if you come from a statistical language like R or Stata, or if you're used to working in MATLAB, that kind of distinction between give me just the true values and, oh, I'm sitting into these locations is something that you sort of internalized, even if you didn't know how to explain it.
Thank you.
Thank you.
All right. Cool. Time for another break? Okay. We're going to, such enthusiasm. So we're going to start again at 4 o'clock. All right. Before we get to actually doing actual computation, so far we've created arrays manually and we've sliced and indexed and did fancy indexing. It's super important, but in a minute we're actually going to do computations on arrays and between arrays and talk a little bit more about what happens there. But before we get there, I thought we should take a few minutes to reason a little bit about what happens when we have more than 2 dimensions, right? So NumPy arrays, remember the type is called ND arrays, the N for variable n more than 2, any number of dimensions, so multi-dimensional arrays. So what I have drawn on screen here is 4 different arrays, a 1, 2, 3, and 4-dimensional array. Pardon my drawing of a 4-dimensional array. I have difficulty visualizing the 4th dimension. So what I do, I just 4D is 2 cubes side by side, 5D is cubes on top of each other, 6D is cubes sort of layer back, and then 7D is like cubes of cubes of cubes of cubes. So I'm sure I'm the only one like this in here. All right, so I have these cubes, these arrays drawn on screen here. On top, I have sort of reference systems, coordinate systems, where there's an arrow pointing in a certain dimension. So if we start with the first one, and the 0 is the 0 refers in this case to the number 4, which is the first element of the shape. Then if I go to 2D, notice how the reference system sort of rotates, where the 0 now points down to the first element of the shape, meaning that in a 2D array, the first element of the shape refers to rows, and the second one, the 1, points to the columns. And then when we go to 3D, the first element of the shape is now pointing the depth. So 0 is the depth, 2 is the height, 4 is the number of columns. And then when we go to 4 dimensions, the 0 is across cubes is the first dimension. Then the 3 is the depth of each cube, the 2 is the height of each cube, and the 4th is the width or the number of columns. So the way to reason about this is that whenever we add dimensions, we basically push down existing ones and we prepend new dimensions. That's a common pattern in what's called row major libraries or languages. So that's how NumPy does it. If you're coming from Fortran or MATLAB, which are column major, your basic element is a column, and then you append a dimension. Every time you add a dimension, you'll add multiple columns, deeper columns, a cube below the original one, basically. So the mental model is sort of entirely flipped. So in a row major library like NumPy, the last dimension is always the columns. And these elements are basically always, more or less always, contiguous in memory as well. So you're pushing down dimensions, the existing ones. One way that I like to think of this is if I have a one-dimensional object, it's kind of like a list. And then the 2D object, it's a list of lists. So here I have 2 lists in the outermost list, and then each of the inner lists has 4 objects. Then here I have 3 lists. Each of them has two lists, 2 rows, and each of those has 4 elements. And then that's a list of lists of numbers. So the 0 keeps on shifting. It's columns first, then rows, then depth, then across cubes, etc. The second reference system at the bottom uses negative values to point to a certain position in the shape. And what you observe is that the -1 is always a row. Right? So this is what I said earlier. The -1 always represents across columns. So the 0 and -1, if you have a one-dimensional array, they point to the same position in the shape. If you have a two-dimensional array, -1 is that 4 here. It's always the number of columns. In a 3-dimensional array, the -1, the 4 here is still the number of columns. And same thing in the 4-dimensional array. So we're going to use that in a little bit when we do reduction operations in our arrays. We're going to have to specify which dimension we want to operate on. And sometimes reasoning in terms of positive position makes sense, and sometimes reasoning in terms of negative positions also helps. So if you're following along, I'll jump through page 37. So there's a section in here about creating arrays. I'll jump over this for now. I think having a human sort of walk you through it is less important than having a human walk you through how calculation works. So on page 37 here, we have rules for computations with arrays or between arrays. Rule number 1 is super important. Is that every time you do operations between arrays, the first thing that NumPy does is to check that their shapes match. The rules for this are called broadcasting rules. Hello? Good. So here are a few examples of shapes that are considered to match. So in the simplest case, let's say we have two arrays like this. So what's the shape of each of these arrays? 3 by 2, that's right. So let's say I add them together. Here the shapes obviously match because they're the same. Right? And what we're going to get is element-wise operation over all the elements of the array. Another array that's considered to be compatible is an array that has, what's the shape of this?
1 by 2.
Yes, only, so this is the part where it's kind of weird to draw on screen, on the board, but I'm considering this to be a 2 comma. So here's a 3 comma and a 2 comma. And what's going to happen here is NumPy is going to basically think of them as like aligning those two shapes starting from the right-hand side, and then it's going to repeat this array. It's going to broadcast this array so that each row, the row here gets subtracted from each row in the original array. So, or added in this case. So if I do this array, I'm going to call it A, and this one is called C. If I add them together, this array here is going to be added to those two rows, added here and added here. And NumPy is going to do this without allocating extra memory to like make them exactly the same shape. So if you have arrays like this that are compatible, one of them is smaller but is a subset of the other one, basically, NumPy is going to be able to operate between those two arrays and do the right broadcasting, do the right repetition of the array, but without having to duplicate, making a copy of the memory to make the array the same shape. Yeah.
So if I took a 3 by 2 array A and added a scalar, it would add it to every element.
Yes.
If I give it something that is the same shape as the row, then
You're doing row, but doing this movement.
row-wise.
Do you mean, when you do this, do you mean row or do you mean column?
That's a good question.
Okay, so the third one, which we'll just repeat what you said. So if I have a single number here, it's another, NumPy also considers that to be a possible case of broadcasting. It would add the 2 to every single element. That one, usually people are not too surprised with. But this one where you're, let's say I have an array that's a 4 by 5 by 2, and another array that's a 5 by 2. That will work fine. NumPy will broadcast this 2 array 4 times, basically, for all of the elements in the other one. I will not go through all of the details of broadcasting. There's a really good, I'll put the link in the Slack channel, and eventually in the YouTube video maybe, to the NumPy documentation that explain broadcasting. But for the exercises we're going to do, and for today, we're going to limit ourselves to these 3 cases, exactly the same shape, one which is an array which is a subset of another one, and then a single value. Yes?
Well, I thought he was going to ask what happens if you have a 1 by 3 column that you wanted to add. Does that work?
Okay, yeah. So if you have a 3 by 2 and a 1 by 2, that's fine, because it can repeat. The one here is repeatable, like you can just do 1 3 times and you're going to get the same thing. But if you get a 3 by 2 and a 2 comma 1, that doesn't work. So this one here is actually a column array, and that's not a compatible shape.
Yeah, no, it would have to, yeah.
That would work fine. Yeah, if it's a 3 comma 1, that's fine.
Yeah. Okay.
I guess, just continue on that, I think the question is, so if it's one single, like a 2, and it needs to be on the row side, will it adjust it?
Mm-mm.
So we'll have to make it 3 by 1, force it to be 3 by 1.
So if I haven't, just to be,
So if C was 3, for example, your C
Here, if it's 3, that's not going to work because this is too big. You're going to get a... You're going to get something.
Is this a consequence of the row order of this? In other words, 4 by 5 by 2 says I have 4 things. Each of them is a 5 by 2. Therefore, I can broadcast 5 by 2s throughout that. Or I could say it's a 4 by 5 by 2 and I want to just add something with the 2 in the last dimension. That's okay too. So in other words, it's kind of right to left. As long as it matches the dimensions from right to left. It can easily be propagated.
So the question is...
The way the things are laid out.
Yeah, if I understand correctly, the question is this broadcasting a consequence of being row major? No, there's nothing stopping you from doing this if it's column major, but instead of aligning on the right-hand side, you will align on the left-hand side.
You can do that?
Yeah, as far as I know, MATLAB has implemented this after seeing it done in NumPy.
So you're not constrained.
So the idea is there's no point in duplicating that memory. Like the idea of broadcasting is to make things fast without allocating more memory than necessary. You're just repeating exactly the same data. So what's happening is NumPy makes sure the shapes match, and it basically does a for loop for us in C. Instead of creating 2 arrays of exactly the same size and then doing for loops, yeah.
Let me just confuse the issue and then we'll move on.
Okay.
4 by 5 by 2. Can I do something with a 4 by 5 and broadcast it?
No, if you do something with a 4 by 5, that will not work,
Okay.
but a 4 by 5 by 1 will be okay.
Okay.
The 4 by 1 by 2 will be okay.
Would be okay as well. So 4 by 1 by 2 would be okay. A 4 by 1 by 1 would be okay. A 1 by 5 by 1 would be okay.
Because the sizes are less than or equal to that dimension.
Yeah. Yes.
If you have a 6 by 6 by 6 matrix and then you want to do something with a 6 by 6 subset, how do you know which columns and rows would be enough?
Okay, this is the last one. So if I have a 6 by 6 by 6 and another one that's a 6 by 6, how do I know how that's going to work? They always align to the right-hand side?
That's what I was saying.
Yeah. Okay. Those are very good questions, but I think we should move on. So you can come to me afterwards with all of your X by Y by Z's and we can discuss. Or you can also just try it. I wanted to do I still have this? All right, A plus B. I just wanted to show you what happens if it's not supported. So I have a 5 by 5 and a 3 comma. If it doesn't work, NumPy will fail loudly with the value error, and it'll tell you these shapes cannot be broadcasted together. It's not supported. And then it's for you to decide, like, oh yeah, because I'm not supposed to add them together, or oh, sometimes it's a hint that like you dropped data or you thought that you had data from 2 sources that actually didn't have the same number of samples, but you thought they did. Sometimes it's just frustrating, but it's preventing you from doing a mistake also. That was just rule number 1. Now the other ones are easy. So that was rule number 1, shapes have to match. Rule number 2, all of the mathematical operators and the universal functions, the ufuncs, that are just a simple transformation like sine, logarithm, exponentiation, etc., they all apply element by element. Right? So if you have 2 arrays, you'll get element-wise operations. Rule number 3, which is going to be the main focus of this section actually, is all the reduction operations, like the mean, the sum, all the statistical moments, they apply to the whole array unless we specify what's called an axis. Why not call it a dimension? I don't know. But unless you specify an axis to operate over. So this means that by default, it will take the entire array and shrink it into a single value. And then rule number 4 is if there's a missing value in your array. So if there's one of those nans that I talked about earlier, it will propagate. I think of nans a little bit like poison. They're very important poison because they signify something important, missingness, but they have the side effect of if you try to add a nan to something, the result is nan. So if you try to compute the sum of any kind of array with a nan, then it'll sort of add to its neighbor, and then it'll be nan, and then it'll add itself to its neighbor, is going to be nan as well, and then you end up with just a single nan at the end. NumPy has a handful of nan functions of reduction operations called nan sum, nan max, nan min, etc. That will ignore the nans basically and prevent them from poisoning the well and give you actual numerical values. All right, so let.
About rule number 3, can you do the fancy indexing, like just sum of those index that I determined earlier?
Yes. The question is, can you do fancy indexing and then compute a sum? Certainly. So my array A was this. We had our, right, I want a sum. So I have my array A. I want the sum of all the numbers divisible by 3. So this is how everything is done in NumPy, basically. You have an array, you make a mask to select a subset of that array, and then you do a computation on that subset. So, yeah.
When you say axis, it feels like it can only have one dimension.
Yes, I'm getting there. So let's see the application of this rule number 3 about the axis keyword. So my starting point is this 2-dimensional array. It's a 2 by 3. And the first call that I make, I call a method. So who knows what a method is? Okay, cool. So quick lesson on methods versus functions. Who knows what a function is? Okay, that doesn't add up to 100%, but it'll be okay. So my array A has some values in there. So NP, the NP prefix, sum is a function that is inside of NumPy, and it acts only on the data that I'm passing to the sum function. So that's a function. This other sum here, I'm calling it a method because it acts on the data stored in the array A, and it doesn't itself take any arguments. It's attached to my array A, and it does computation on whatever that array stores. Store is a loose term here. But that's the basic difference. The function will act only on what you put in there, and the method is attached to an object, and it will do computation based on the data that that object contains. Why use one versus the other? Doesn't matter so much. I tend to use the sum method the methods more often than the functions. In the beginning of NumPy, like 15 years ago, 20 years ago or something, there was only functions, and then sometimes in the last 10 or 15 years, they added these methods. One is a little bit less typing than the other, which gives it an edge, I guess. Yeah.
Can you apply np.sum to 2 objects of type A?
That's a good question. Can I apply np.sum to 2 objects? So the answer to that is always read the docs. So if I look at the documentation for np.sum, it takes one positional argument A, one array, and then this axis keyword that we're going to talk about. And A has to be array-like, which is a common thing in NumPy to mean anything that could be converted to an array. So like a list is array-like, a list of lists is also array-like, a list of tuples, a tuple of lists, et cetera, et cetera. So no, it has to be one at a time. All right, so first example, I'm calling sum on my array A, and it by default it takes all the data and collapses it into a single value. And the unless here was unless I specify one of these keywords called axis. And axis is the dimension that will be collapsed, or the axis that will be collapsed. So here I started with an array that's a 2 by 3. And I specified axis equals 0. So I'm operating along axis 0, and that dimension is going to get collapsed. I'm going to end up with only 3 values. I'm going to use that in a second. And in the second example, I'm specifying a negative axis. Just like everywhere else where you would pass an index in Python, you can pass a positive index from the beginning relative to the beginning, or a negative index relative to the end. Here we're specifying axis equals -1, so we're starting from the end of the shape, so we're summing across columns, we're collapsing all the columns into a single value. Hello? Yes. So a way to think about the axis keyword, so if I have an array that's a 2 by 3, and I specify axis equals 0, what happens is that axis will go away, and I'm going to end up with something that's a 3 comma. If I have an array that's a 2 by 5 by 7 by 2 by 4, I'm starting easy here. And I do axis equals 0, 1, 2, 3. So that's a 3. The output of this will be, that was a terrible example, I'm sorry, 2, 5, 2, 2, 4. Right? The one that I'm specifying is the one that goes away. I'm going to go back to a smaller one here, 3 by 4 by 5. If I say axis equals -1, the result is a 3 by 4. Yes?
Can I use a tuple for axis also, like sum over several at the same time?
Can I use a tuple for the axis? No, it has to be an integer.
Okay, so I have to do that several times.
Yeah. One at a time.
So your axis is kind of like a group by statement in SQL. It's telling how you want to aggregate.
The axis is kind of like a group by statement in SQL. Yeah. I never thought of it this way, because but you're going to like pandas tomorrow. Yeah, sort of. It breaks my mind a little bit because so the arrays have the requirement of being like it's always full, like it's always more like a cube and like a box. Whereas if you do a group by, each group could be a variable size, which wouldn't really work. But like the idea is close enough where like if you have a table in a database and you do a group by, you're basically splitting your table into multiple groups. It's kind of like reshaping it to say like this is group 1, this is group B. I'm going to put them one behind the other. And then I'm going to sum or do whatever that way so I end up with just one table. So yes, it's kind of like a group by. Yeah, if that helps you, it's like a group by. Yes.
So both with C over here and then what you did over there.
Yeah.
Why does 2, 3 become 3 comma? Because doesn't that imply that it's there's 3 rows?
Yeah. So the question is, if I have an object that has a shape 2, 3, and then I sum over one of the axes, what is the result 3 comma or 2 comma? What is the comma there? It's always a shape. It's always a tuple. And remember, it's the comma that makes it a tuple. So that's why I'm always writing it with the comma. I'm talking about the shapes there.
But does that, so you're not saying that it's a 3-column object, you're just saying it's a tuple?
I'm saying it's a 3 comma, which will be a row actually. A row object, not a column object. It's not a 3 comma 1, it's a 3 comma. It's the shape. I'm talking about the shape. So I know you'll I know you will walk out of here and will forget this thing. It took me years to realize that the axis, you specify the axis, the one that you specify goes away. So for years, I did what I'm about to do here. So I'm going to create an array. I'm going to make it 24 elements long. I'm going to reshape it to be a 6 by 4. So what I would do is I would get data from somewhere, whatever I need to work with. I did some simulation, some audio signal that has a certain number of channels, and I would look at the shape of my array and think about it real hard. Be like, okay, I have 6 audio channels, and each of these channels has 4 samples. Right, 6 channels, 4 samples. I want the the mean value of each channel. So how many channels do I have? 6 channels. And then I would go axis equals 1. Oops. And I look at the shape. Let me do it again so it's clear. So I want the mean value of each channel. I would specify some axis that I'm not sure if is the right one, and I would immediately look at the shape. And then I look at this. Is this what I expect? No. I want 6 values, not 4 values. Therefore, I want axis equals 1. And then often I would forget to remove the dot shape, and I would have an error later because I was working with the tuple instead of an array. But I would do something like this, and then I would move on with my day. So this is, you can always fall back to this. I still do that all the time. If I'm working with really big data, really big, like data that doesn't fit on screen, basically. So for some people, that's big data, where there's no point for me to show it on screen. Therefore, I will look at the shape and I'll reason about, like, what does this data mean? How should I work with it? So yeah, look at the shape before, look at the shape after. It's one of the most important and useful attribute on arrays.
Why is it this way around?
So the question is, why? Why? Let me try to help you, or help me too. The y is the axis, the one that gets collapsed. It could be the one that is the one that you keep. Both of them have, or it could be always the last one, but then it's not super flexible because you would have to like reshape stuff every time you want to do anything. Design decision, it fits, I don't know, it's useful. Yeah, he's here this week.
They just flipped the coin.
Maybe that's the way APL did it.
Yeah, it might be how another library did it. It fits my brain, but yeah.
That's where they came from.
So, because is the answer. We're making a good team, you and me. All right, so we have these methods, the axis keyword we're going to use again and again. Like I said, there are function versions and method versions. They work exactly the same way. Both of them take an axis keyword. The function version, you have to pass in the data. You have to pass in the array. On the right-hand side here is a subset of the methods that exist in NumPy. There's much more than that, but those are sort of the most commonly useful one. PTP is peak to peak, is the extent, so it's the difference between the max of the array and the min of the array. Speaking of max and min, I will cover that briefly because they're a little bit special. So they work together, basically. So min and max, they return the min or the max of the array, either for the entire array or for a given row or column or along a given axis. But they don't tell you where that min or that max is. Argmin and argmax are the two other functions that you need to use in order to find the position of that minimum or maximum. And again, both of them exist as a method on the array and as a function.
Why didn't they use the word index instead of arg?
Why index? Why arg and not index?
Gives you the index, right?
Again,
We'll have to ask.
yes, we'll have to dig into old commits on some old version control system, probably. All right, so let's do, instead of doing this little exercise here, we're going to do a bigger one. So in the material that you've downloaded, there is a folder called exercises, a folder called wind statistics, and in there a file called windstatistics.py. So this is just a Python file. So if you're in Canopy, anyone here using Canopy? A few people? Okay. So if you're in Canopy, in order to execute the file, there's a little green triangle up there, which you can just click, and is going to execute the file for you, do %run. And you'll be able to write your solution in the notebook, in the file. Every time you run the file, the output of what you run here will be accessible in the IPython session. If there is, Dylan and I will be walking around and explaining this. If you're using Jupyter, I will create one here.
So if we've already imported NumPy, can't we just say np.loadtext?
Yeah. You can do that. Let me create a new notebook somewhere else. Actually. So if you're using Jupyter, you should navigate to the downloaded materials. So for me, they're down here. And there should be an exercises folder. Click on exercises, then wind statistics. And in there, you'll have the data and the file. And you don't want to open the file. What I recommend you do is go in the create a new notebook by clicking new in the upper right. So Python 3, I'm going to put this on one side, put this on the other, and then execute a magic called loadpy with wind statistics.py, like this. And then if you execute this cell, it's going to load the content of the exercise, and then you're comfortably in Jupyter. You can copy and paste around and solve the exercise. So the file is in exercises, wind statistics, and it's called windstatistics.py. And you're welcome to solve it in any way you want. It's a bit tricky to have all this mixed environment. So Dylan and I will be working around and make sure that you're all set up to work on this. One missing piece of information. So there's a function called load text that it tells you to use. We've already imported it for you. And the only thing you need to pass is the name of the file. The file is called wind.data. So you can basically, I'm running out of space here. This code here on the lower right is enough. It will load the entire data as a NumPy array that you can then work with. So I'm just keeping the important thing in the cell right now. %load will allow you to load the content of the file in the notebook. This will do the import you need. And then load txt will load the data that's on disk as a NumPy array. And then you should be able to walk through the exercise. It's time if you want to finish on time. Sorry. All right, so I'm gonna start by loading my data. So that function is called load txt. My data is called wind.data. And first thing I do usually when I get new data is I look at its shape. So it has 6,000 rows. That's big data, like I said, and 15 columns. This is definitely not going to fit on screen. But at the top, I had an example saying that the first 3 columns contain dates, or the year, month, day, and then the last 12 columns contain the data. So I don't want to keep on slicing all the time throughout my notebook. So I will start off doing a slice to separate the dates. So the dates are all my data, all the rows of my data, but only the first 3 columns. And all my wins are all the rows of my data from column number 3 till the end. And remember, slicing gives me a view of my data. This is super cheap. I'm not using lots of memory. I can make a bunch of slices. I'm not copying anything. But it will make the rest of the code much easier to read instead of seeing data, comma, 3, all the time. So, question number 2. I want the min, max, mean, standard deviation over all locations. I want to collapse the whole thing. So this is I'm just going to do the mean here. I'm going to show the other ones for now, but for the rest, I'm just going to do one at a time. I'm just going to show one to save some space. So wins.min, wins.max, wins.std for standard deviation. All right, so this, because I'm not passing any axis keyword to mean, min, max, and std, it just collapses the whole array into one. So if I print this, I'm getting 4 values. Then question number 3, I want, let's say, the minimum ever recorded, so that's min, at each location over all the days. So I want to collapse the days, and I want to end up with a value per location. So wins has a certain shape, 6,000 rows, 12 columns, and I think I want, so how many values do I want to end up with? 12. So is this axis 0 or 1? I don't know. It's not 1, so it must be the other one. All right? Again, it still works. This is valid. This is a valid way of figuring out which axis it is just try it and reason about the shape. Is this what you expect or not? So it is not axis 1 that I'm looking for. It is axis 0. Then question number 4, I want 1 value per day. And this one, I can reason the same way, or I can reason that it's not 0, therefore it must be 1, right? That's sort of the simple way. It's always good to double check, so I'm gonna axis equals 1, shape, 6,000, yep, that's what I expect, 1 value per row. Question number 5, I want the location that has the greatest wind speed on each day. So each day I want 6,000 or so. I've already figured out which one is 0, which one is 1. If I have 1 value per day, I want axis equals 1. The question here is, what's the method I should use? Max, min, variance, argmax. Yes, argmax with axis equals 1. And finally, it gets interesting here. I want to find when the greatest wind speed was ever recorded. And that's fun. And there are also many ways of doing this. There are at least 3 ways. I can never remember the 4th one. I had a student once come up with a really clever way, but I can't remember. So let's start with 1. Does anyone have a suggestion? So someone says mask, someone says argmax, and someone says argmax of the max. All right, let's start from the bottom. Argmax from the max. So wins dot max along which axis? I disagree, respectfully. Okay. Because if I get the max of the argmax is going to give me a value between, it's going to give me like the highest row number or the highest column number, and I want the opposite thing.
So if you take the max of each of the columns, right, which is for each of the locations, right? Yeah. Vector, that should give you the location within that vector. So that's argmax of max, right?
Yeah, I agree if you say it that way. So I have my table. What I'm going to do is I'm going to collapse it this way. So for every day I'm going to get the max. Every day I'm going to get the max. I'm going to get it with 6,000 values. And then I'm going to find the argmax of that, which is going to give me the row where that happened. So I want to collapse the columns. Collapse along axis 1, just sanity check, yes. And the argmax is row 2161. So that's my row. And the date is, in my dates data, I want the data at that particular row, which is 1966, December 2nd.
So you're inverting, if you did it as a function rather than as a method, you'd invert the order, right? And that's why.
Yeah, I see.
That's why you didn't believe me.
Yeah. Yes, if it was a function, if I was written as a function, I would have to do np.argmax of np.max of wins axis equals 1.
And if you play back the recording, which is now on tape, you'll see.
Okay. I bow.
Can you back up just previous to that last part, where you have the row number and then you feed it into dates? You try to do that again?
Yeah. So row is some value. My dates is a slice that I've made earlier that contains only the first 3 columns, and I'm interested interested in a particular row of which I want all columns, which is this selection here. So that's technique number 1. Technique number 2 is I don't care about that this array is multidimensional. I just want the argmax, which gives us this number, which is obviously the linear index of the position of this maximum. Then you can do this dance to be like, okay, so I can do a floor division by the number of columns. Bullseye, this never happens. I got it right the first time. This never works. You're guaranteed to write a bug when doing this. But yeah, I got it right. But there's a function in NumPy that can do this for us called unravel index, which does this neat things where you give it an index or a list of indices and the dimensions or the shape of the array that you want to, where it was taken from, basically, and it's going to return a tuple of where that number is. So I could do unravel index of wins.argmax. Given that I'm in an array of a certain shape, tells me row 2161, column 11. And that would be column. I'm just going to do it here, but I will need to import NumPy as NP. It hasn't been imported as NP above. So that would also work. And the last one with the mask is arguably the best one. I'll give you that. So the idea is, given some wins, I want to find out where it's equal to wins.max. Max. Oh, this is so hard. And somewhere in here, there must be a true because there must be a max. And I can use either so np.where or this other one that we worked with before called non-zero. They do the same thing in this case. It returns a tuple of arrays with the coordinates basically of all the maxima. So it is the most powerful because it gives you, if there are multiple maxima, it'll give you the position of all of them. But it is the easiest one, the hardest one to understand. And like, what do I get out of this? You get a tuple of arrays. Those are row indices, and these are column indices. So I could use this code here to say rows and columns is equal to where. So I'm just going to call it row. But so all 3 of these solutions would give me December 2nd, 1966.
Can you put that in square bracket notation too?
Can I put, what do you mean?
Could you call that row by putting that mask in square bracket rotation?
Here? The row, so the row, all the variables I called row here, I can use, they'll all give me more or less the same response on line 106.
But could you put like dates, square bracket, mask, and pull that row? To give you the
Have nothing.
To give you the day, the date.
This mask, no, because this mask is 2D, it would give me the value. It would not give me, if I use the result, if I use this, it'll give me the masks. But that's not what I'm interested in this case. I'm actually interested in where it is, not what it is. All right, and last but not least, I want the average wind speed in January per location. So we got to break this apart. First, I need a definition of what's a January. Thanks, autocomplete. So January is what? Which rows are January rows? Yeah. So I have two data structures now, a dates array and a winds array. Winds array doesn't know anything about time, not useful. Dates array is this guy over here. And the second column represents the month. And it uses one base indexing for the month. So I can do dates, all the rows of column 2, column 1. Thanks for catching my error. Whenever that is equal to true, then that's the month of January. All right, so if I look at this mask here, it's true, 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 and then false at the end. Even without looking at all the data, I'm reasonably confident that it's doing the right thing. And then, given my wins, I can reuse that January mask. I can do that even though I computed my mask on another object. Because the mask has the same number of rows as my wins data, that's fair game. So all the rows, only a subset of the rows where this mask is true, all the columns, and I want the mean. This is the last time I will ask you. The means one value per column, one value per location. Is that, should I specify axis 0 or axis 1? Yes, so 0 or 1, that's 0. So I want to collapse my table this way. This is axis 0 is the one that I want to get rid of. So I specify axis equals 0 here. I'm going to print that, and that's it. So these values here are my average wind speeds in January for the 12 Irish cities where this was measured. Yes, I could use -2. That is correct. Good job. Yep. But it's not bad. I agree. -2. It's both of them are useful. Both of them exist for a reason, because sometimes you don't know ahead of time how much data you're going to have, and sometimes you don't know. It might be deeper than you think, or shallower. Your array might be shallower or deeper than you think, have more or fewer dimensions, and using negative indices always gives you relative to the end. So not a bad idea. And with this, the day is over. Congratulations. This should get you, give you a good foundation of reasoning about NumPy arrays. This axis keyword is everywhere. Thinking about slicing, thinking about indexing, the fact that being aware of what gives you a copy, what gives you a view is also super important. There's a little bit more stuff in these slides if you want to look at them. Talking a little bit about broadcasting. There's also a little bit of a discussion about how reshaping works and how it's a cheap operation because it doesn't copy data either. It just reshaped the interpretation of the memory into a new array. But yeah, that should give you a solid foundation, and NumPy is one of those packages with awesome documentation, so that's also a good place to look at. So thanks for today. I hope you learned a thing or two, and I'll be here if you have any questions. So, thanks.